Hello, this is Dr. Muhammad, and this is the course of Design of Steel Structures according to AISC. And still we are dealing with beam column. And today I'm going to talk about the contents of today's lecture is going to be related to the concept of braced and unbraced frames. And then I'm going to talk about the amplification factor, B1, which is commonly used for the moments occurring in the member when it is braced against side sway. This is the case where we are having side sway prevented. So we are going to amplify the moment, as we said before, using some factors. So today I'm going to focus on this amplification factor B1. And after that I'm going to work out an example to highlight and explain the main idea of this amplification factor and how we can take into consideration the moment or additional moment related to this factor. Okay, so let's go now to the definition, or we can say the concept of braced and unbraced frames in general. Whenever that we are talking about braced and unbraced frames, we need to keep in our mind something related to the relative movement between the 2 points of the column or the element itself. So if we are having the 2 points, they are not going to move to one another, then in this case we call this case braced frame or braced case. And if the point is moving with respect to other end, if one end is moving with respect to the other end, then in this case we call it side sway case, or we can say unbraced case. All of them, they are okay. So this is braced and this is unbraced. This is side sway permitted. This is, we call it side sway prevented. Okay, so you are going to find in different textbooks different titles for this: braced case, side sway prevented case, and sometimes they call it NT. They call it no translation, no translational case. So this is like 3 different names for the same concept, which is the 2 ends are not moving to one another. However, for the side sway permitted, we call this side sway permitted or unbraced case, or LT, which is going to be lateral translation case. Okay, so this is also another name. So we have, as I said, like 3 names now for the same concept we are talking about. Sometimes the designation of this in the code or specification is different even than this. They are giving for anything that is braced, for example, they give it the designation of 1 as subscript, for example, and for anything that is lateral translational or side sway permitted or unbraced case, it is giving it the subscript 2 or the designation of 2 and whatever. So this is something you are going to find it in the specification itself. This is in the specs or the specifications. You are going to find they are using these 1 and 2 numbers in order to keep in our mind whether the system or this element in a braced case or in a braced frame or in unbraced frame. Okay, so these are the different names that you're going to find in different textbooks and the specification as well. So at the end, because of this, as we said and mentioned in the last or the previous lecture, we said that we have 2 types of amplification that we need to take into consideration. The first one is related to the element itself, where that there is buckling would take place or occur due to the axial load. And this buckling going to have the maximum amplitude at the center of the element itself. And we put this designation, which is small delta, and we call this case to be P delta or small delta effect. So this is the first effect that we have, and we are going to account for this case with taking into consideration the amplification factor B1. Okay, remember that we have mentioned about the different ways for taking into consideration the second order effect, and we said there are different methods. The specification already addressed in the appendices, and there is one method related to the amplification of the moments. So now we are dealing with the amplification of moments in detail, because this is the simplest and maybe most commonly used procedure. So the first amplification is going to take, or we are going to consider it for the moments that is going to come from basically the no translational case, or the braced case, or sidesway prevented case. Okay, and this is going to be designated with P small delta. The other case, it is going to be P capital or uppercase delta. Okay, so this is going to, as you can see here, delta is going to be at one end of the element, and P, or the axial force, is going to be applied. This is going to be taken into consideration by a factor called B2. We are going to amplify the moments by B2, which is here, to account for the effect of side sway case, which is P delta, capital delta. This is for steel frames in general. For those who are interested in concrete, you can find the same approach is used also in reinforced concrete elements. If you are going to visit ACI 318, for example, version 2008 or later version, I think also they are using the same procedure and the same philosophy for amplification of the moments, whether due to, or in the case of braced or unbraced. So we are taking into consideration two factors, B1 and B2. Okay, now let's go and see what is the required moment strength here. If we are having M ultimate coming from the loads being applied on the system or in the element, this means that our ultimate strength, which is the required moment strength, need to be amplified in a specific way. And this specific way is going to take into consideration two things, okay? Two effects. Effect that is coming from B1 and the effect coming from B2. This means that P delta, small delta, this is P delta, right? So we have two effects here. So based on this, we are to approximate these two effects, two amplification factors, B1 and B2, are used for the two types of moments. So we are going to use this B1 and B2 for two types of moment. The first one is going to be designated with M NT, and the second is going to be designated with M LT. So NT, as I said, no translation. It means braced case, side sway prevented. Okay, this is synonyms of NT. And LT means that lateral translational case, which is the case where that we are having the side sway permitted. Okay, so how we are going to take this into consideration? We are going to take it into consideration as you can see here in this equation. We are going to say that the required moment strength is going to be composed, or is composing or consisting of two components. The first component is related to the no translational case moment, and the second is related to the lateral translational case moment. The first moment is going to be amplified by factor called B1, as we said, to take into consideration P small delta. And the second moment, or lateral translation, is going to be used to amplify the moment, or the lateral translational moment, to take into consideration P capital delta. So the two effects now are going to be taken into consideration by using two different amplification factors, and they are going to be applied in two different types of moment. One related to no translational case, and the other is lateral translational case. Okay. Okay, and this is the final the final definition for B1 and B2. B1 is amplification factor for the moments, amplification factor for the moments occurring in the member when it is braced. Take care of this word. Against sidesway. And B2, the amplification factor for moments occurring when it is not braced. So remember the B2 for not braced, B1 it is related to the braced, B1 is related to P small delta, B2 related to P capital delta. Okay, I hope that you have an idea now of what we are going to do in the next slides and the next step after that. Okay, so commonly whenever that we are going to have or calculate the required strength, we have an idea now of what is B1 and B2. Okay, from the previous slide we have an idea about this. This is going to take into consideration P delta, this is going to take into consideration P delta, small, and this is large. Okay, but the point is, what is the definition of no translational moment and the definition of lateral translation moment? We want a specific interpretation or understanding for this type of moment. Let's start with MNT, which is the no translational moment. It is the maximum moment assuming that no side sway occur. So if we have something like this, and we have bracing, for example, here, for example, and we have this is the element, the beam column element, let's assume. Okay, so whenever that we have moment, then the maximum moment, assuming that no side sway occurs, whether the frame is actually braced or not, So if we have another case, the frame is not braced here. Okay, moment frames, for example, moment frames. Okay, so no translational means that even that we have like translational load on this element, and we have gravity loads being applied here, the moment, the portion of the moment that is going to come from the gravity loads only, okay, if we have here also gravity loads, the moment that is going to come from this gravity load, vertical load, we are going to designate it with MNT. So whether that we are having braced frame or not braced frame or unbraced frame, okay, that's the meaning of NT. No translational means that MNT will be factored load for load moment for LRFD and a service load moment for ASD, as we know. But remember, this load that we are talking about, service load, okay, or factored load, it is related to what? The gravity load only. Gravity, okay? Gravity load. It is not related at all to any translational load. So for example, if you are designing cross-section or structure, and you have two cases, two different cases, one related to 1 point dead plus 1.6 live, for example, and the other case is related to, another case is related to, for example, 1 point dead plus something live plus wind, for example, or something like this. There is wind here or earthquake. Then we are going to look to the first load combination and say that all the loads here are gravity load, vertical load. Then the moments that is going to be developed here, we call it MNT. And for the case of load combination 2, when we are going to study load combination 2 or the lateral load combination, we are going to say we have two different components of moment. One type which is related to the gravity load, we're going to call this MNT, and there is one type which is related to the lateral load, and this is what we're going to call it MLT, as we are going to explain it in a minute. Okay, you understand? So here, this is the meaning of MNT, the moments coming from the gravity load, or in more specific, moments coming from no translational or no translation movement or motion of not motion. Motion means that we are going to be in dynamic, but the meaning here, no translational, means that the two end points of the element are not going to move to one another, relative to one another. This won't happen unless there is wind load or earthquake, for example. Okay. Now, the maximum MLT, it is the maximum moment caused by side sway. The subscript LT is for lateral translation. This moment can be caused by lateral loads or by unbalanced gravity loads. What is the meaning of this? Let me clear everything here. So if we have lateral loads, then we are going to expect that the structure is going to have some delta here. The moments that is going to be developed due to this lateral load, whether it is earthquake or wind or whatever, we're going to call it MLT, which is lateral translation. Sometimes if we have symmetric structure, we have symmetric structure, but we have unsymmetric loading, for example, loading coming from here. Unsymmetric loading, something like this, for example. Then we're going to have some lateral component that is going to be developed in terms of the translation. So in this case, the source of this MLT is going to be whether there is direct lateral load, horizontal, or there is indirect horizontal load coming from unsymmetric gravity loading or unsymmetric system. If we have unsymmetric system, for example, for some way or another, it is not symmetric. Means that we have something that is making our system is not symmetric. So this moment is going to be, as we said, caused by lateral loads or by unbalanced gravity loads. Gravity load can produce side sway if the frame is unsymmetrical or if the gravity loads are unsymmetrically placed. So if we have gravity loads here, symmetric gravity loads, but the system itself is not symmetric. There might be lateral loads in this case would be developed. So these are the two cases that we have. Whether it is lateral loads or unbalanced gravity loads, or gravity load can produce side sway if the frame is unsymmetrical or if the gravity loads are unsymmetrically placed, as I said here. MLT will be 0 if the frame is actually braced. That's right. So we are expecting that always MLT is going to equal 0 if the system or the frame is braced. For LRFD, MLT will be factored load moment. For AISD, it will be service load moment, as we know. And then again, we put here the definition of B1 and B2, the amplification factor for the moments occurring in the member when it is braced against side sway. Means that, as I said, remember well, the two ends are not going to move to one another. But B2, it is the opposite, where that the amplification, it is the amplification factor for the moments resulting from side sway, if there is movement, relative movement between the 2 points. Now let's go to the required axial strength. Before we were talking about what we call it the required moment strength, right? That we are going to amplify the moment. But here we found that there is something else needs to be amplified as well, which is the required axial strength. The required axial strength. We found that if we have a system, and this system, there are some loads being applied here, and there are some loads, for example, here, that is going to be applied on the system. We found that the no translation axial forces are going to be, okay, no problem for us, okay, but I mean that it is going to be taken into consideration because PNT, the no translational case, is going to be the axial load corresponding to the braced condition. If we have braced condition, for example, then we are going to have the axial strength or required strength in the member itself. It is going to be coming from the gravity load, okay, or other type of loading. Maybe it is going to be horizontal loading also, but it will be tension and compression here, for example, if we are talking about like overturning moment. So anyway, if the two points, okay, are going to be maintained together, then there is no problem with the required strength. This delta, small delta, would not make anything, would not affect the required axial strength. However, the large delta, which is, if we make something like this, large delta, which is this delta, for the translational case, it is going to make some problem for us. Not problem, it needs to, in this case, we need to amplify the required axial load corresponding to the sidesway condition. Okay, so let's read it here. In addition to the required moment strength, the required axial strength must account for second order effects. Okay, so axial loads also we need to take into consideration the second order effects. The required axial strength is affected by the displaced geometry of the structure during loading. That's important here, keyword here, displaced geometry. Okay, this is not an issue with member displaced with small delta. So it is not concerned with, as I said here, it's not concerned with the small delta. It will not affect the required axial strength. However, if the element is going to move laterally, one end of the element moving laterally, this delta is going to make an effect on the required axial strength. So we need to amplify P, which is the axial load corresponding to the side sway condition. Again, this is, remember, it is axial load, not lateral load. It is axial load. PLT, it is axial load. But due to side sway condition, when there is lateral loading, like wind or earthquake, for example. Okay. But it is not with the joint displacement delta, means that we need to take into consideration this big delta. The required axial compression surface compression strength is given by, this is the equation that we need to take into consideration here, which is PNT plus B2 times PLT. PNT and PLT, both of them, they are axial load. One coming from braced condition, other coming from the side sway condition. Okay, so remember that well. Okay. Now let's go to B1, which is the amplification factor for the moments occurring in the member when it is braced against side sway. Okay, this is, as we said many times, it is going to take into consideration P small delta effect. P small delta effect. Okay, now let's go and see here. So here we are having single curvature case, and after that I'm going to talk about the reverse curvature. So we have two cases here for the moment. We found that we need to know where the maximum amplitude of buckling would take place along the element. So we found something that is interesting, or at least there is a difference between two cases. We found that whenever that we have single curvature of the element, commonly the maximum delta is going to occur at the middle. However, that if we have double curvature, like as you can see here, for example, we do not know exactly where this delta is going to occur. Okay, it is not going to be in the middle. It is going to be somewhere. Okay? So whenever that we have reverse curvature, we found that we need to amplify the amplification due to the P small, due to the P delta effect in general, in case of the double curvature or reverse curvature. I mean, here in the single curvature, we are sure and we know that it is going to be in the middle. So no problem here. No problem. We are going to use the same equation for obtaining B1. But we found that if the moment is going to be with double curvature, we found that this B1 needs to be multiplied or amplified. Okay, so we need to multiply it by another factor, which we call it Cm. Okay, so it is this Cm is a factor that is going to take into consideration the case of reverse curvature here. So in the reverse curvature, we are going to use Cm, and in case of single curvature, we are going to put the Cm1. Okay, so that's the case. That's the case that we want to highlight here. Okay, so now let's go and see the understanding of this. Maximum moment amplification occurs at the center where the deflection is largest. For equal end moments, if we have equal end moments like this and this here, okay, M node and M node, the moment is constant through the length of the member. As you can see, the moment is constant, and it's going to be amplified only at the middle with P delta, as we said, throughout the length of the member. So the maximum primary moment also occurs at the center. So still, if we have the ends to have 0 moments, maximum moment is in the middle. If we have equal moment at the top and bottom, then we are having the maximum moment, we're expecting it to occur in the middle. Thus, the maximum secondary moment and maximum primary moment are additive. Additive means that they are going to be added to one another. We know that the maximum secondary moment, which is due to P delta, and the maximum primary, okay, moment are going to be in the same point, which is the center. But actually, when there is double curvature, the maximum deflection is going to be at the center, for example, but the maximum moment will not, okay, won't be. So even if the end moments are not equal, if we say the end moments are not equal, as long as one is clockwise and the other is counterclockwise, there will be single curvature bending. So that's the point here. If we are having single curvature, even that we have one clockwise, for example, like this, and the other one is going to be counterclockwise. This is clockwise and this is counterclockwise. This is, for example, M1, let's assume equals 100. This is M2, for example, let's assume it equals 200. In this case also no problem for us. Why? Because the curvature is going to be, okay, the curvature is going to be in the middle, okay, almost in the middle. Okay, almost in the middle. It's not going to be in the middle exactly, okay? It is going to be in the middle. And the maximum, okay, the maximum deflection and the maximum moment is going to be on the same, almost in the same point. For example, if we have like moment like this and this, for example, maybe the deflection is going to be, okay, the deflection is going to be, for example, let's assume it is here, okay. The maximum deflection, as they said, that will be single curvature, and the maximum primary and secondary moments will occur near each other. So they are going to be here the maximum, because we have here M1 and here M2, so we are not sure exactly where the moment is going to be. The maximum moment is going to be. In this case, the maximum moment coming from the primary maximum moment and the amplified or the secondary moment are going to be near to one another. So the idea here is we have single curvature. The structure or the element is going to bend in one direction, one side. The other case that would happen, and we want to take it into consideration, would that we have exactly like reverse curvature, like double curvature, we call it reverse. The maximum primary moment is at one of the ends, okay, like here for example. Here we have the maximum moment, plus this is P delta, this is due to P delta. As you can see, this is the shape for us. This is the primary moment, and this is P delta. Then we are going to have something like, after superposition, we're going to have something, as you can see. So maybe the moment, the maximum moment would be maybe here. In this case, the maximum moment will be here at the end. But if the moment here is having like more curvature here, like this one, the maximum moment will be here, okay, at this point. So it is different. The maximum moment is going to be here. So it depends on whether the maximum moment will be at the end, M maximum equal to M2, or M maximum is larger than M2, which is M2 is the end moment here. So it depends, right? So depending on the value of the axial load P, the amplified moment can be either larger or smaller than the end moment. And this is right. And the main reason here, the axial load P that is going to be there, it depends on it, depending on the value of this P. The amplified moment can be either larger or smaller than the end moment. So if I ask you, what is the reason for having the moment at the end or within the member in case of reverse curvature? So the main reason is P, the value of B, the value of P. The maximum moment in a beam column therefore depends on the distribution of bending moment within the member. So based on that, we need to take into consideration the distribution of moment. We need to know how the moment is going to be distributed here. Okay, this means we need investigation. In order to take into consideration this concept that we have said now, or explained now, we need to take this distribution into account. This distribution is accounted for by a factor. This factor is going to be called Cm. Okay, and this factor is going to be applied to the amplification factor given by, this is the amplification factor, do you remember? 1 over 1 minus P ultimate over PE. Ultimate load over Euler load. So we're going to multiply it by Cm. Okay, so this is the case of the reverse curvature. Based on that, we are going to have B1 is going to equal the equation that we have had before, which is related to 1 over 1 minus PR over PE1, but we are going to use two factors here. One factor, which is Cm, to take into consideration the moment gradient or the distribution of moment along the element, and alpha, it is another parameter that is going to be used to account for the type of design, whether it is LRFD or ASD. So now we have B1 is going to take into consideration everything. Cm, this means takes into consideration moment distribution. 1 minus alpha times PR over PE1. Alpha, it is going to be based on the type of the design, whether it is LRFD or ASD. If it's LRFD, then it is 1 as usual, because we have obtained B1 based on factored load. If not, then we need to use ASD for example, then we're going to use 1.6 for alpha. And then PR and PE1, PR it is the required axial load, and PE1 it is the Euler load. Okay, Euler load. Okay. And this PR, it is going to be whether P ultimate for LRFD or P actual or applied for ASD. This is PR that we are going to use here. Okay. And this PE1, it is going to be Euler, like Euler load. It is pi squared EI over K1L to the power 2. Okay. So this is how we can calculate B1. I hope now you have understood what I want you to understand. This is the equation. Every factor now is important for us to know. Remember well that B1, okay, must be always equal than or larger, equal to or larger than 1, because it is amplification factor. We are multiplying it by the moment. This means that we need to find it larger than 1. If we calculated and we found that it is less than 1, this means that we should take it as 1. Okay, so 1, it is the minimum value for B1. After that, we are going to repeat the part related to the required axial strengths. Already I have mentioned about it. So here, according to AISC context, PR is going to equal PNT plus B2 times PLT. We know what is the meaning of PNT and PLT. The important thing that both of them are axial load. Okay, one is related to the braced, one is related to unbraced or sidesway condition. Okay, and as approximation, this is as an approximation, we can take this PR to equal PNT plus PLT. Okay, as an approximation, we take it like this, like we neglect the effect, because actually, as I said, we are using B2 here only. B1 is not going to take or not going to affect the required strengths, as I have explained 2 slides back, right? But B2 will, because P delta, big delta, is going to have an effect on the required strengths. Okay, so for simplicity and for as an approximation, PR can be taken with this without any amplification. The amplification actually is important for moments. It is most important for moments. Okay, the moment of inertia I and the effective length factor K1 are for the axis of bending, and K1 equal 1 unless a more accurate value is computed. So K1 taken as 1 always, unless that you know better information about this. Note that throughout chapter C of the specification, the subscript 1, okay, corresponds to the braced condition, and the subscript 2 corresponds to the unbraced condition, and I have mentioned about this before. Okay, now how to evaluate CM? So now for CM, the factor, okay, evaluation of CM, the factor CM applies only to the braced condition, as we said. Okay, the CM, we're talking about the braced condition. There are 2 categories of members: those with transverse loads applied between the ends, and those with no transverse loads. So if we look here, we are having 2 cases actually. We have, as we said, unbraced condition where there is no bracing, and we have another case which is braced condition. Okay, in the braced condition, what we are going to find that we are going to find some cases where that lateral load is going to be applied along the length of the element. So this is, we call it braced with transverse loading. And here this one is going to be braced but with no transverse loads, So we have 2 cases here, and CM needs to distinguish between the 2 cases here, okay, for this member, which is member AB. Okay, if we're talking about this member, if there is no transverse loads acting on the member, okay, then CM is going to be calculated from this equation. This equation, actually, you can say it is empirical equation, but we have M1 over M2. What is M1 and M2 here? Okay, it is the end moments that we are going to find at the ends of the member. Okay, as you can see it here in front of you here, we have cases where that there is single curvature, and here we have like double curvature or reverse curvature. Whenever the element is going to have single curvature, M1 over M2 is important. It is important to know that it is going to give us negative value. So here we are going to have negative value. But here M1 over M2 should always give us positive value. Positive value. So Cm is function of not only the values of M1 and M2, but it is the ratio between the two. It is important. The ratio, it is what important, not the absolute value. So if we say that 100 M1 and M2, for example, 200, it equals to, as if we're talking about 10 over 20. So the absolute value is not making effect on Cm, but the ratio what really makes the effect. The ratio between the upper and lower, or the end moments of the element. And the other issue is the value of the ratio, whether it is positive or negative. It depends. If our structure or the element is going to have single curvature like this, so the moments are going to have opposite sense, as you can see here, then it is negative. Remember that opposite senses, they are negative. If they are going to be having the same sense, here it is clockwise, for example, here it is counterclockwise, then it is going to be positive. It is going to be positive. Okay, so M1 over M2 is a ratio of the bending moment at the ends of the member. M1 is the end moment that is smaller in absolute value. That's important. And M2 is the larger. So we're talking about the absolute value here. So we are talking about the M1 and M2. What is how we can put them? It is not related to their sign. It is related to which one is smaller, okay, and which one is going to be larger in absolute value. So this is going to be smaller, and this is going to be the larger, okay, the larger one. M1 over M2. We need it to be always having less than 1 value, because we are going to multiply it by 0.4, and then we are going to subtract it from 0.6. So commonly Cm is going to be in this range. Okay, so M2 is the larger, and the ratio is positive for members bent in reverse curvature, as we said here, and negative for single curvature, as we can see. Reverse curvature, a positive ratio occurs when M1 and M2 are both clockwise or counterclockwise, as we mentioned here. Okay, so remember well, positive, negative. Okay, now let's go to, this is some values actually for some moments. If we have M1 equal to M2, which both of them are equal, and they are, as you can see here, they are having the same sense. Okay, they are having the same sense. In this case, this is going to be, okay, it is going to be positive, as we said, so it is positive here, and this is 1 because the ratio is going to be M over M. Okay, so that's the case here. Here, for example, we have M and 0, so it is the smaller value is 0 and the larger one is 1, so it is going to be cancelled here. It is going to be 0.6. If we have the same M over M, then in this case we are going to have Cm equals to 1, and because we are going to have the equation to be 0.4, it is going to be 0.6 plus 0.4 in this case, so it is going to give us 1. And Cm is going to be, for this case, if we have M here and 0.5 M, for example, so here it is 0.5 over M, so it is half here, positive because they are in the same sense. This means that Cm is going to be 0.4. Okay, 0.4. So this means that, what is the meaning of 0.4 here? It means that B1 is going to be multiplied by 0.4, means that we are going to reduce the amplified moment by 60%. Can you imagine? So can you imagine how much Cm is important? Okay, Cm is an important factor for beam column, as we were using for CB, for example, before. Right. So it is taking into consideration the moment distribution and where the maximum moment is going to occur. Okay. Okay. Now let's go to the next case. So remember that the first case was if there is no transverse loads acting on the member. But now let's go to the case where that there is transverse loading is going to occur in the member. If we have the member here and we have something here, okay, or if the member horizontal and it has distributed load, for example. So this is transversely loaded members. Cm can be taken as 1. So conservatively you can take it as 1. Otherwise, a more refined procedure for for this case is provided in section C2, okay, in the commentary to the specification. So it is Cm is going to be reduced, okay. So conservatively you can take it as 1. This is better for you if you need to have a quick judgment on the member. But if not, if you want to go accurately, then you can reduce the Cm by this factor and alpha, whether that you are LRFD or ASD, and PR and PE1, as we have explained before. So for simply supported members, this parameter is going to be calculated, as you can see here, pi squared delta node EI over M node L squared. Okay, where that delta node is the maximum deflection resulting from the transverse loading, and M node is the maximum moment between the supports resulting from the transverse loading. Okay, and actually this factor, it has been evaluated for several common conditions. It's better to visit this table C-C2.1. Actually, I found that in 2005, the specification AISC 2005, this is the table here, and you can find this factor for reduction of Cm, and you can find Cm as well for different cases of laterally or transversely loaded members. For example, concentrated load here, you can find this minus 0.2 here. It needs to be calculated in this, based on this form. And here you can find it in 2016. I found this in table C-A-8.1. This is the name of the table. This is, you can find it in 2016. And also are going to find the same, the case and this parameter, and then Cm is going to be calculated also or given to you. It is similar to this. They are almost similar, but only the title or the name of the table is different between 2005 and 2016. Okay, now let's go to the last part, which is example, and let's see how we are going to proceed with this example. The member shown in this figure, okay, is part of braced. Take care of this. Braced means what? Yes, exactly. 2 points are not going to move to one another. They are braced. By some way, they are braced. Service loads are shown. We have dead load 70 kips, live load 210. This is the axial load. Okay, this is from the top. Okay, and of course from the bottom it is the same. Okay, it is the top and bottom. They are axial load. And then we have moment at the top, dead load and live load, and we have moment at the bottom, dead load and live load. They are different, as you can see. Okay, so we have like different moment. Okay, different moment. It is something, for example, something like this. Okay, okay. The cross section is 12 by 65. Length is 14. The grade of this element is 50. And is this member adequate? This is a question for you. Considering that the KXL equal to KYL equal to 14 means that it is K, whether X or Y, it is going to equal 1. Okay. Okay, so we want to check whether it is this beam column. Now it is a beam column, right? Because we have axial load. It's the first time now to see something like this. We have axial load and we have moments, different moments at the ends. We won't check, and they said that it is braced. This means that we are going to use B1 only. B2 is not an issue now for us. Okay, there is no amplification for the moment due to lateral translation. Only we need to obtain B1. Okay, so the strategy is we are going to go and check for the column part of the beam column, and then the beam part of the beam column, and then check for B1, and then we get the M required, or MR, and if we are talking about the whether it is ASD or LRFD, so MR, and then check this moment with the maximum allowed moment coming from the tables and charts of beams and columns and so on. This is the steps that we are going to follow in order to see whether that this member is adequate or not. Okay, let's go and see this. So first of all, we need to go through the factored load in detail and see what are the moments that is going to be along the member, because we need to calculate, if you remember CB and so on, we need the moments to be calculated at each or different places. So the factored load computed from AISC load combination 2, it is gravity loading only. We are here using gravity loading. Why? Because they didn't mention anything about lateral loading. We have gravity loading only. Okay. Determine which interaction formula to apply, because we have two different interaction formula. Do you remember? We have one with 8/9 multiplied by the moment term, and there is another one which is half multiplied by this, exactly the axial part, and then this part is okay as it is. So we need to know which interaction equation that we need to use in the beginning, okay, or we should use. So we are going to calculate, do you remember the equation that is going to have the or give us the which equation that we should use? Do you remember? It is P ultimate over phi c times Pn, and we should compare it with 0.2. If it's larger than 0.2, this means that the axial force component is more dominant. Okay, and in this case we are not going to reduce the axial force, we're going to reduce slightly the moment. But if it's less than 0.2, this means that we are going to use the other equation. Okay, the other equation. Okay, so first of all, we need to know what is what is this P ultimate, okay? P ultimate over phi c Pn. We want to know this. P ultimate, it is known, given for us using the gravity load condition 1.2 dead plus 1.6 life, we can obtain the axial load, the maximum axial load, right? If we go back here, we have 70, and so multiply this 1.2, this is 1.4, and you are going to get the value for you 420. So we have 420 over, we want to get phi c Pn. What is the quickest way for obtaining this? Yes, that's right. You can obtain it from different sources, okay? But from the simplest way is to use the column load tables. You are going to use the column load tables and enter with the length that you have. You have 14 here, 14 feet, right? So you're going to go into the tables and then go with 14 and then check what is the case for you. Sorry, this is not, this is for, sorry, we are talking about column tables here. So we're going to have the table like this, and you have numbers, and then go with 14 and check what is the value that is related to the cross section that we have. We have W12 by 65, right? So we're going to go the table, which is for wide flange, table 4-1, available strengths in axial compression and kips. We're going to go W12 because we have our section to be 12 by 65. If yield 50, it is given for us, and then 12 by 65 here. Then we are going to the most left column, which is the length of the effective length with respect to the least radius of gyration, which is related to Ry, and then we're going to find the length here. This is ky times ly. We have it 14 because we have k, it equals to 1 in our case. Go horizontally, and you are going to find that phi c pn equal to, for LRFD, it is going to be 685. 685. Then we're going to use it here. 685. This is the condition that we need to get, right? When we get the ratio, it is 0.6 larger than 0.2. This means that we need to use equation H1 1a, which is slightly reducing the moment term, right? This is the equation. Let's go to the equation here and see what we are going to have. First of all, we need this term. Already this term has been calculated. Now we want to go to the other terms, and this is the main important part for us for today. M ultimate x. M ultimate means that the required moment strength in x direction, right? This means that we need to obtain it. This means that B1 is going to be used here for augmentation, and in the same time we want phi be mnx, which is the flexure strength of the moment. In this case, we are going to bring this from the charts the most easiest way, and this can be calculated by calculating B1 and multiply it by the ultimate moment that we have. Okay, I think this part is going to be 0 for us, right? We do not have any moment in perpendicular to the plane that we are in the plane, okay, perpendicular to the plane that we are talking about. Okay, so now let's go and see what we are going to do first. Now, if you remember, for this M ultimate, we need, as I said, we need to obtain B1. B1, it equals to Cm here and 1 minus alpha, right, times there is PR here and PE1. Do you remember in the denominator there is PR and PE1? So we need to calculate this PE1 first. Okay, let's yes. So this is here for P1 B1, it equals to Cm over alpha times PR over PE1, and there is 1 here, right? So we need to calculate PE1 first, okay, and then PR and then Cm. Okay, now let's go back again. So the first thing we need for B, we need this PR, we need PE1, we need Cm, we need to know alpha, which is already it is known for us if we are talking about LRFD. So let's go one by one to see how we can obtain it. So PE1, it is Euler load. Okay, PE1, it is Euler load. Pi squared EI over K1L. K1, which is Kx or Ky, it is 1 here. And we are going to multiply by 12 because we are converting from foot to inches. When you calculate this small rational, you are going to find that it gives you this value, 5,405 kips. This is PE1. Then let's go now and obtain Cm. What is Cm for us? Let's go here. Cm equals to, from the equation that I have explained a few slides ago, 0.6 minus 0.4 times m1 over m2, right? Let's concentrate now. We have m1 and m2. Remember, m1, it should be the smaller one. m2, it should be the larger one. So we have 70.8 over 82.4. Okay, so this is positive or negative? Think about it. They are in the opposite directions, so it would be negative in this case. So we're going to put it here negative. If you substitute here, you will get 0.9. Cm is going to be 0.9. What is the meaning of this? What is the meaning of 0.9 for something? It means that B1, the amplification factor, is going to be reduced by 10% or 6% something, which is the difference between 0.94 and 1. So we have B1 in this case would equal to Cm, calculated before, alpha, it is going to be 1.0 if we're talking about LRFD, PR, which is going to be our P ultimate because we are talking about the LRFD, right, which is 420, already we have calculated before, and PE1 already we have calculated in the previous step, which is 5,000 something, right? That's it. So we can obtain B1 now. We can obtain B1. Look here, this is B1, 1.023. What is the meaning of this? This means that the moment will be amplified by 2.3%. That's it, B1. Only the moment is going to be this is the delta, so we are going to have P delta effect is going to only give or add 2.3%. That's it. So what about this one? We don't have this reverse. We have single curvature. So in this case we are going to have the negative part, which is the negative ratio between M1 and M2. M1 and M2. Okay? So I hope that you could understand what I'm talking about here, because it is, if you could understand it, you're going to find it easy to go through the beam column examples in general. Okay, now let's go to the next part, which is related to 4 beams, which is the part related to the beams. If you remember before, we said that for beams we need to be careful, right? We need to be careful because we have something called CB. We have something called CB, and this CB is going to be computed first, because whenever that we are going into the design charts, we need to be careful that CB there is always 1. However, we need to calculate CB for our case based on the bending moments that we have along the beam itself. Okay, so let's go again, not to lose what we are doing. We already calculated this part, and we have already calculated the augmented part here, which is already we have done in the previous slide. And then the last thing is we want to know what is the phi b m n x, right, which is the flexural strength of the beam. For the flexural strength of the beam, we are going into the charts. Do you remember the charts that we have used before? So we're going to use these charts. These charts are for CB equal to 1. But actually CB for our case is going to be different. We have moment gradient here. Do you remember? Whenever we have moment gradient, this means that we need to use CB larger than 1, right? So in this case, we are going to use the beam design charts because it is easy for us to use it. CB equal 1 and LB given in the example to be 14 feet. The moment strength is going to be 345 phi b times mn foot per kips. From the charts, please pause the video here, bring your manual and check this value. Okay, 345. Okay, I'm considering that you are going to pause the video now. Okay, after checking by yourself, you can come and check this here. This is the what you are going to find in the charts. Going with table 3-10 wide flange shapes, which we call it available moment versus unbraced strengths, and then you are going down here with 14 feet, and then going and hitting this curve, which is related to our cross section, which is W12 by 65. Okay, you're going to find it here. Go horizontally, you're going to find 345. This is the LRFD phi b mn. Okay, so I hope that you got it as we have obtained it. Okay, now let's go to the next part, which is related to CB. As we said, the charts give us CB equal to 1. Now we need to obtain the real value of CB. How we can obtain it? From this equation, that I have explained it maybe 3-4 videos before. 12.5 M maximum over the denominator, 2.5 M maximum, MA, MB, MC. What is MA and MB and MC? It is here. This is A. Okay, we have here, this is A, B, C. Okay, and M maximum that we have here. In our case, M maximum is going to be 82.4, which is at the bottom here, 82.4. Okay, this is going to be our maximum moment, and it's going to be here also. These values, M, A, B, C, you can obtain it from the moment diagram that you can obtain it easily. You can draw it from the bending moment diagram. Okay, calculating CB, after calculation we found that CB equal to 1.06. What is the meaning of this? This means that the flexural strength of the beam part of the beam column is going to be magnified by 6%. So this 345 is going to be magnified by 106. It's going to be 366 kips. This is the supposedly the flexural strength, right? Okay, but we need to check something important here. This is CB times the phi MN based on our CB, but this value should not exceed what? The plastic limit. Do you remember? We have plastic limit here. If our shape is compact, then this is the plastic limit, yielding, okay? But if not, the horizontal one is going to be the flange local buckling limit for us, right? That's an important issue. So let's go to the chart and check what is the horizontal line here, larger than 366 or less than. Let's go here and see. So if you go, you're going to find this is the horizontal line here, and it is 356. 356. 356, it could be plastic limit or flange local buckling. It depends on the element itself, whether it is compact or non-compact. Okay? If you go to this element or this section, you're going to find that it is non-compact in the dimensions and properties table. And based on this, we're going to find that W12 by 65 is non-compact. This means that the horizontal line in these charts indicates flange local buckling, not plastic moment. Okay? If you do not understand what I'm saying, please revisit one of my videos like 2 weeks ago. You're going to understand what I'm talking about. Okay? Okay, now let's go back again. We found that it is 356, the maximum flange local buckling from the charts. It is less than 366. This means that the flexure strength of this cross section is going to be 356. 356. It will not reach 366. It must be 356. Okay, this is why. What is the reason for this? Because W12 by 65 is non-compact for F yield equal to 50. Okay, can you see this? Can you check this from where we can get this W12 by 65 is non-compact? Okay, let us check here. If you go to, this is the dimension and properties table, the dimension and properties table, you're going to find here for this cross section that we're talking about, W12 by 65, you're going to find that F here, there is F note, footnote here, F. This footnote, F, for the cross section says that the shape is non-compact. The shape is non-compact, written here. Shape exceeds compact limit for flexure with F yield equal to 50, which is our case. Okay, so you can check this piece of information from this table, table 1-1 for wide flange shapes, and this is the dimensions table. Okay. Okay. Now we are here. We are here. So we found that CB is going to be 1.06. In this case, the maximum flexure strength for the beam is going to be 356, not 366. the factored load moments are going to be M and T. It is 82.4 foot kips, and MLT, the lateral translational moment, there is nothing. We are having nothing here. It is 0, right? This would give us, this would brings us to the equation for augmentation. Remember that what we want now, what we want is the augmentation of the moment, right? Because in this equation, this part already we have calculated, but now we are dealing with this part. We want to obtain this part, which is, as we said, it is going to be 356, right? So based on that, we are going to have MNT. We are talking about MNT here, right? Because we are not having any translational moment. So MR, the required strength based on the AISC equation C-1A, the required moment strength is going to be MR equal to M ultimate, which is B1 times MNT plus B2 times MLT. We do not have here, we do not have lateral moment. This means that this term we are going to use it. This means that 1.023, this is B1, times 82.4, which is the maximum moment that we have at the bottom of the element. This gives us this value, 84.3 kips. And we call this the M ultimate X. This is what we are going to use simply in our equation, right? So the flexure strength from the charts after the story of the CB, we know it. Here, the augmented moment or the required strength after obtaining B1, we could obtain it. And then this term already we have obtained it in the very first beginning. Based on this, we can, if we substitute in this equation, you can find that it equals to 0.824, which is less than 1. This means that this member, or this W12 by 65 wide flange, is adequate. It is adequate. Okay, remember, Will, that this element, this cross section, it is, the shape is has a footnote. So the design moment strength shown in the table, okay, which is this table, this is the trick of this example. The horizontal line here for this cross section is going to be flange local buckling, because the shape is what? Non-compact. From where I got that it is non-compact? From the dimensions and properties table. It gives us, it has a note or a footnote. It says that it is non-compact. Okay, and you can find it here. Thank you, and this is what I should say for this today's lecture. Thank you, and see you in the next video.